Hello there, students. In this video, we're going to take a look at our first example using the Biot-Savart equation by looking at the circular loop problem. Suppose we had a wire loop that had a current running through it. Let's choose the current to be flowing clockwise. We know that this current will make a magnetic flux density, or B field, in all space. But for this problem, let's only concern ourselves with solving for the B field at the center of the loop. Our starting point is the differential form of the Biot-Savart equation we saw in a previous video. And now let's label our diagram with all of these vectors and variables. Our current loop has a radius capital R. Our clockwise current makes our vector dl look like this, since it will always be tangent to the circle and in the direction of current flow. Then, our vector r, which points to the center of the circle, to where we are calculating the B field. This vector r starts at our infinitesimal wire segment where vector dl is. These two vectors, vector dl and vector r, will always be perpendicular to each other as we integrate around the circular loop. This means if we were to take the magnitude of the cross product, where we would normally get dl times r times the sine of the angle between them, theta, since theta is always 90 degrees, sine of theta is always equal to 1. Using the right-hand rule for currents, or evaluating the cross product with any coordinate system, we determine that the direction of the B field produced by this current at the center of the loop will be pointing into the screen. We represent a vector direction into the screen using this symbol, which is supposed to represent the fletching of an arrow, since it is facing away from you. For a vector pointing out of the screen or towards you, you would see the arrow head. In this case, we represent such a vector with a symbol like this. Outside of the ring, the B field is indeed pointing out of the screen, and anywhere inside the ring, the B field is pointing into the screen. So we might put the symbols on our diagram something like this. For the rest of this video, though, we're only going to concern ourselves with the magnitude of the B field and not its direction, since we've already handled that. As a magnitude, we're left with this differential equation. To get the full B field, we need to integrate both sides like so. The circle on the integral symbol is indicating that we are traversing the entire path of a closed loop, in this case, the wire loop itself. This integral is really simple. All the integration is telling us to do is start at one point of the circular current loop, walk along the loop until we get back to where we started, and report how long that was. This is just a fancy way of saying the circumference of the circular current loop. Another way to see this is to start at the center of the current loop, where we are calculating the B field. To integrate around the loop in cylindrical coordinates, we need to first integrate along the radial direction. Our wire only exists at a single value along this radial integration, which is reflected by this Dirac delta function. Then, we need to integrate the angle from 0 to 2 pi so that we get the entire length of the wire. Sure enough, we get the same result. Simplifying this result, we get the common equation for the B field at the center of a current loop. In the next video, we'll step up the difficulty with another example using the Biot-Savart equation. Until then, thanks for watching and learning about physics. If you have any questions or want to see a specific topic, leave a comment below or head over to my Facebook page in the video description.